Hey guys, we are starting off right in the computer today. I hope yesterday's lesson about properties of atoms and subatomic particles found you well. Hope that was a nice transition into the regular curriculum with chemistry since we had done that before. We are going to break some new ground today though. So as we go through this, it's super important that you send me questions, give me feedback. Is the workload too much? Is it not enough? Is it difficult to access? Would you like some information in a different way? So on and so forth. And I'll start going through your assignments later today and tomorrow and just making sure everyone's staying on top of them. And so with that, we're going to jump into talking about compounds, the mole, and molar mass. Very important concepts in chemistry. All right, so here are some learning objectives for you. I'd want you to be able to describe the difference between an element and a compound, explain the concept of the mole, which is a tricky one, and we'll see how we do with this as time goes on. But again, super important in chemistry. And then lastly, I want you to be able to calculate the molar mass of a compound by the end of this. And I will do some examples of calculating molar mass on the whiteboard at the end of the video. And then just a technical note, if you could please start actually submitting assignments in Schoology, it would make my ability to track them much easier. I know that's contrary to what I said in the classroom, but different times call for different measures. Thank you for that. All right, so here we go. First off, what is a compound? Yesterday we talked about elements being the purest form of matter. Compound is the next up in the line of purity. Compounds are two or more elements bonded together in whole number ratios. That idea of whole number ratios is important. That means we can write compounds as chemical formulas with whole numbers, with integers after them. So an example of this would be like water. Water, H2O, is a compound of 2 hydrogen atoms per 1 oxygen atom. Again, those are whole numbers, the ratios in which the elements are appearing. Molecules are the microscopic units that make up compounds, the microscopic particles. So when we say that atoms make elements, molecules make up compounds. And then lastly, the least pure form of matter would be mixtures. Mixtures are made if you take elements or compounds and mix them at any ratio. We're not going to spend too much time with mixtures. They do come in two forms, homogeneous and heterogeneous. And I think it's a PD question on your assignment to figure out what the difference between homogeneous and heterogeneous is. You might have some ideas just by looking at these pictures and give some examples of those. One example of a mixture, this one would be homogeneous, is salt water. Salt water is a mixture that can be 10% sodium chloride and 90% water. Or I could make a mixture that was 9.2% sodium chloride, salt, and 90.8% water. So those mixtures can happen at any ratio, which makes them different than compounds where elements are bonded at whole number ratios. When it comes to writing compounds, we use chemical formulas. So compounds are written with chemical formulas which use elemental symbols with subscripted numbers to express the amount of atoms of the element that comes before the number. That's very important. We see that in water. The 2 in H2O is talking about hydrogen, not oxygen. So here's water. We've got 2 hydrogens, 1 oxygen, and that's why we write it H2O. This is ammonia. Here we see 1 nitrogen, 3 hydrogens, so we'd write this one NH3. Here's carbon dioxide, 1 carbon, 2 oxygens, so we'd write that CO2. And then lastly, here's methane, which is carbon, 1 carbon, and 4 hydrogens, so we write that CH4. If no number is written, we assume it is 1. We see that in water. We don't write H2O1 because there's no number after the O. We just assume it's 1. We know there's only 1 oxygen. And then lastly, and this part's a little tricky, so it's important to pay attention here. If a chemical formula uses parentheses, then the number after the parentheses should be distributed inside the parentheses. So here is an example. This is copper phosphate. In this particular chemical formula, we do see parentheses that kind of box in this phosphate ion, and PO4 is two elements, phosphorus and oxygen. We've got one phosphorus and four oxygen, and that one phosphorus and four oxygen, they travel together as a group. And then in this chemical formula, we're saying we have two PO4s. So if I actually wanted to count the number of atoms of each element in this, copper is not inside the parentheses, so it's just got its three. But when it comes to counting the phosphorus and the oxygen, I need to consider both the numbers inside the parentheses and the number outside. So there's only one phosphorus. I know that because there's no number written after it. So the 2 distributes in. 2 times 1 means in total there's 2 phosphorus. And then the oxygen, so 4 after it. And there's 2 outside, so 2 times 4 means in total there's 8 oxygen. 2 PO4s means 2 phosphorus, 8 oxygen. Which brings us to a very important concept in chemistry, and we're going to spend a while talking about this over the course of the next few weeks. It'll come up a lot, but as just an introduction to the mole, if you get confused about this, there's 100+ websites, articles, YouTube videos you can watch of different people trying to explain the concept of the mole. Here's my take on it, but feel free to do more research as needed. The mole is an important unit in chemistry used to count a very large amount of things like atoms or molecules. So when it comes to chemistry, it's very important that we count stuff. We know how many atoms we have of a certain substance, or we know how many molecules we have of a certain substance. And the mole is the way that we do that. Because these things, atoms and molecules, are very, very small, we created this huge counting number, and we use that to figure out how many things we have. So the way I would think of a mole is it's like a dozen. If you have 12 eggs, you have 1 dozen eggs. If you have 24 eggs, you have 2 dozen eggs. When it comes to the mole, if you have 6.02 times 10 to the 23rd atoms or molecules, then you'd say you have 1 mole. 6.02 times 10 to the 23rd, which is a huge number, 602 sextillion, huge number, is equal to 1 mole. And this also allows us, the mole allows us to count by weighing things, which is the next step we're going to go to. The mole is a bridge between counting and weighing, because chemists can't possibly count this many atoms and molecules. So our way around it is to find the mass of things and then use conversions to get from mass to number of things. And so that brings us to the molar mass. Molar mass of a substance is the mass in grams per mole of 1 mole of the substance, or of 6.02 times 10 to the 23rd particles of that substance. So first of all, let's just think about this in terms of dozens. If I had a dozen tennis balls are lighter than baseballs, so a dozen tennis balls might weigh 3 kilograms. And I might write that as 3 kilograms per dozen. A different substance, baseballs, which are heavier, might have 8 kilograms per dozen. So different substances can have different masses for the same amount of things. And that's what the molar mass is. It's how much does this set amount of things weigh? And that set amount is 6.02 times 10 to the 23rd. For every element, the molar mass is simply the atomic mass on the element of the element found on the periodic table expressed in grams. When you look on the periodic table and you see hydrogen has an atomic mass of 1, oxygen has an atomic mass of 16, that is telling you in atomic mass units how much one atom of that element weighs, or it's telling you in grams how much 6.02 times 10 to the 23rd atoms weigh. So we're able to make that jump from microscopic to macroscopic by making the switch in units from atomic mass units when we're talking about individual atoms to grams when we're talking about moles, the large scale. For a compound, the molar mass is the atomic masses found on the periodic table of all the elements of all the atoms of all the elements added together. So what I mean by that is, let's take methane for example again. CH4. CH4 is made up of 1 carbon, 4 hydrogens. If I wanted to find the molar mass of CH4, then what I need to do is find the atomic mass of C, which is 12.01, and then I need to add it to the atomic mass of hydrogen times 4, and that times 4 is because I have 4 of them. So the 12.01 from the carbon plus the 1.01 from hydrogen times 4, because I have 4 of them, gives me the molar mass of methane, CH4, which is 16.05 grams per mole. So that's telling me if I took methane and I weighed out 16.05 grams, then that would be equal to 1 mole, and it would also be equal to 6.02 times 10 to the 23rd molecules of CH4. So what I've done effectively is I've weighed something and I've used its weight to count how many things I have in that sample. And with that, I'm going to go to the whiteboard and I'm going to do a couple examples of figuring out how many atoms there are of each element in a compound. And then using those same examples, I'm also going to show you how to find the molar mass using your periodic table. So when you go to the whiteboard and you watch those examples, and when you go to do the assignments, make sure you have a calculator, make sure you have a periodic table, and just know that this is a very, very important skill in chemistry, one you'll definitely have to use a lot once you take chemistry. So stick with it. Send me questions as you have them, and be well.
Hey guys, you just heard me talk a lot about compounds, the mole, and molar mass inside the computer. We're here at the whiteboard now. I just want to do a couple examples of what you're going to have to do for today's assignment, which includes counting up the number of atoms of each element in a compound and then determining the molar mass, or the mass of 6.02 times 10 to the 23rd particles of that compound. So these are two very important fundamental skills in chemistry literacy. You're going to pick them up real fast. I'm going to do 3 examples here. The first one, sodium hydroxide. Second one, iron 3 chloride. And the last one, calcium phosphate. They're kind of in increasing difficulty. As I go through these, I certainly make sure that I have my periodic table on hand because I'm pulling atomic masses from that. And I'm also using a calculator. I'm just using Desmos, but you can use whatever calculator you've got. And let's have at it. So the first one I'm going to do here is sodium hydroxide, NaOH. It's a lie. If you go to a hardware store, it's probably one of the most produced chemicals in the world these days. And the first thing I want to figure out is how many atoms of each element are there in this compound. So know how there are no numbers here. If there's no numbers after each element, then I just assume it to be 1. And so I see one element here, Na. I see one element here, O, and I see one element here, H. I know that because each starts with a capital letter. A is not its own element because it's lowercase. Na is an element. So what I've got here are 1 sodium, I've got 1 oxygen, and I've got 1 hydrogen. Those are my atoms of each element in this compound NaOH. And now if I want to find the molar mass, I need to know how much each of those weighs. So I reference my periodic table. And for this, I'm happy if you want to just round to the nearest tenth, let's say. I look at my periodic table and I'm looking for the atomic mass of each of these elements, which is the mass that one atom weighs in atomic mass units, or it's the mass that 1 mole weighs in grams. So if we're talking on the microscopic scale, we're using the units atomic mass units, or Daltons. When we're talking on the macroscopic scale, which is really relevant to chemists because things happen on our scale, on the large scale, we're talking in grams and moles. Remember, a mole is just a counting unit. That means 6.02 times 10 to the 23rd things, particles, atoms, molecules. So when I look on my periodic table, I see that the mass of one sodium atom is 23.0 atomic mass units, but the mass of a mole of sodium atoms is 23.0 grams. I go back to my periodic table. I see that the mass of one oxygen atom is 16.0 grams. Or excuse me, the mass of one oxygen atom is 16.0 atomic mass units. The mass of one mole of oxygen atoms is 16.0 grams. And then lastly, hydrogen. The mass of one hydrogen atom is 1 atomic mass unit. The mass of one mole of hydrogen atoms is 1 gram. So I know what the individual components weigh from the periodic table. I know how many of each of those individual components there are. So now I can just add them all up. And what I get here is 3 plus 6 plus 1 is 10. Carry the 1. 3 plus 1 is 4. I get that the molar mass of sodium hydroxide, NaOH, equals 40.0 grams per mole. In other words, if I had 6.02 times 10 to the 23rd, this huge number of sodium hydroxide molecules, then it would weigh 40 grams. And this is important because it's going to allow us to go from weighing things to counting things, because that's how chemists count, is they count by weighing, because you can't simply count individual molecules. So that was one example, pretty straightforward. Again, the atomic masses of the individual atoms added together gives me the molar mass. Let's do another example. Alright, on this next one, I've got iron chloride, iron 3 chloride, FeCl3. So the first thing I'm going to do is I'm going to count my elements and how many atoms of each. There's nothing after Fe, so I have 1 iron atom. There is a 3 after Cl, so I have 3 chlorine atoms. Now that 3 does become important here. First I'm going to just find how much does 1 mole of iron atoms weigh. When I look on my periodic table, I see that 1 mole of iron atoms is 56.0 grams. And then I'm going to ask myself, how much does 1 mole of chlorine atoms weigh? Here it's 35.5 grams. But notice how I have 3. So what I actually have to do to this number is I have to multiply it by 3, because this was the mass of just 1 chlorine atom, but I have 3 in this compound. So I'm going to multiply this number by 3. And I get 106.5. So that's the mass of 3 moles of chlorine atoms. So now I can just add that. This is times 1, technically, because I only had 1. So I can just bring over that 56. And now I can add these two together. And I get the molar mass of FeCl3 is 162.5 grams per mole. Again, I'm just adding up the weights of the individual components. Here this one's a little different because one element had 3 atoms, and so I had to take its atomic mass and multiply by 3. But other than that, just adding up the individual components. Let's do one more example. Pause the screen now if you want to look at the work. Alright, this last one is a doozy because it's got parentheses. Ca3 in parentheses PO4 2. So the parentheses mean that this thing, PO4, comes as a packet. We actually call that phosphate, which we'll get to down the road. Phosphate comes as a packet, even though it's made up of 2 different elements, 1 phosphorus and 4 oxygen. That 1 phosphorus and those 4 oxygen are sticking together. And in this compound, I have 2 PO4s. So how you could think about this for the sake of right now is take that 2 and rainbow it in, distribute it into the parentheses similar to how you would in algebra class. If I have 2 PO4s, then that means I still have my Ca3 because that is not inside the parentheses, so the 2 does not apply. When I come inside the parentheses and I rainbow that in, 2 times 1, the invisible 1 on phosphorus, is 2, and 2 times 4, the 4 on oxygen, is 8. So that's kind of an expanded version of this chemical formula. You might wonder, well, why don't they just write it like that in the beginning? Again, that's because phosphate comes as a packet. It's important that we write it as PO4, and we'll get to that down the road. But for right now, in calculating molar masses, I think it's helpful to distribute that 2 in to the parentheses and then write it out as one simplified formula. So now that I've got this Ca3P2O8, I know how many of each of these elements I have. So I'm going to make a little table here. The elements are Ca, P, and O. The amount of each element is 3 calcium, 2 phosphorus, and 8 oxygen. The weight of the single element I'm going to get from the periodic table. So a single calcium is 40.1. A single phosphorus is 31.0. And a single oxygen is 16.0. Right, so I get the mass of those atoms from the periodic table, and then I'm just multiplying the amount times the mass. So I'm going to put a multiplication symbol in there to get the total mass of that element. Again, turning my calculator for this. 3 times 40.1 equals 120.3. Two times 31, 62. And 8 times 16 is 128. So those are my masses, total masses from each individual element. And then if I want the total mass of the compound, I just add these three numbers up and see what I come up with. Got 120.3 plus 62 plus 128 equals 310.3 grams per mole. So 1 mole of this amount, or 1 mole of this compound, weighs that amount. You can see that as the compound gets bigger and bigger, the molar mass gets bigger and bigger. It weighs more to have the same amount of things. And so pause the screen again if you want to see the work on that. Here I used a strategy to stay organized by making that table. Certainly do what works for you. And if you have any questions, please send them my way. If the workload is feeling like too much, not enough, give me that feedback as well. And we'll get through this. Thanks, guys. See ya.